Hey, what's going on, folks? It's Mike here, and welcome back to the Programming Language First Impression series, the series in which we look at a programming language for the first time for about an hour together, just see how easy it is to get set up, what the ecosystem looks like, what the language is like, and hopefully learn a little bit more about programming. And with this lesson, well, you guessed it. For those of you who've been following along, we looked at CPP2 in the last episode, so let's just do it. Let's just go all in and let's take a look at the Carbon programming language. Now, for those of you who don't know, Carbon is another experimental successor language to C++. And I'm really excited to look at this language here. I'm going to go ahead and start off with a wiki page here just to give us a little bit of context. And as far as I know about Carbon, it's probably just as much as you folks know if you've been attending or watching various C++ conference videos on what's been released about Carbon. That's where I've seen it personally, in person or online, talking about this language, which was first announced in July of 2022 at CP+ North, as mentioned here. And that was a really big and exciting announcement, I think, in the C++ world. During this time, July, and then we got CPP2, which we talked about in the previous video from Herb Sutter. And of course, this is coming in an effort from Chandler Carruth from Google and a bunch of other engineers. Actually, it's not just him. He made the announcement or the talk, but there are several other folks credited with leading this initiative and have been contributing to this project. So I'm really excited to dig into this and just see what's new about Carbon, as well. C++ is in a really exciting state in the sense that it's been a language that's constantly evolving, but folks are now looking at, can we do the sort of thing that happened with JavaScript, where you build TypeScript or several other variations, I should say, that compile down to the original language and then generate the assembly code and so on. And I think that's a really interesting story. So again, I'm going to be curious about learning with Carbon with you folks. Again, as mentioned, an experimental programming language designed for connectiveness with C++. And I believe that has to do with the interop story, with being able to use and mix Carbon code with C++. So as mentioned, this project is very young. It is a programming language. I don't believe it's out, or we're going to see what the state of it is. I do have Godbolt open, so we will be able to try some code, so don't fear. But we'll try to build this thing and just see how to get it set up here. So anyways, in 2022 of July, so not too long ago, that's basically 2 years to this recording, he stated that Carbon was going to be created to be a C++ successor. And there's supposed to be a minimal viable product version 0.1 in 2025 and a production-ready version around 2027. Okay, so those are the goals that we're going to hit, but we're not far away from a version 0.1, which folks could probably download. I'm assuming that means we'll have like a binary release or something that we can install like on a package manager or something, which is really cool. So anyways, the language is going to intend to fix several perceived shortcomings of C++. Again, interesting language there. And that is kind of interesting because, again, if we're following this series, if you've been watching these episodes, the shortcomings indeed are sometimes their strengths, right? The freedom that you have with C++, sometimes their weaknesses, right? There's too much freedom, right? So again, it's just kind of an interesting thing as we've been looking at different languages. Every language has a trade-off, but Carbon's trying to improve, this ecosystem or experience in some way. But otherwise, let's see, it's going to provide a similar feature set. And the main goals of this language are readability and bidirectional interoperability. Okay, so this ability to write C++ code and Carbon code and basically mix them freely. I'm not sure, this is going to be the thing that I'm interested in, if Carbon is going to compile down to C++, which we saw with CPP2, for instance, in the previous video, if you want to watch that. I'm not sure if that's the story or if it's just like a ABI compatible thing or what exactly they're thinking about. Again, when I'm looking at this language, same thing with CPP2. I'll just give the caveat that this is very early. It could change. This video could be irrelevant, by 2027. So, but it is interesting to see this evolution here. Okay, so let's see. So it's got this bidirectional interoperability, which allows the user to include C++ code in the Carbon file. Cool. As opposed to using a new language like Rust that, whilst being influenced by C++, is not two-way compatible with C++ programs. Okay, interesting. Changes to the language will be decided by the Carbon leads. Okay, so there is some committee and folks, actively building this. I think we'll see a little bit on the wiki page. Let's see some examples here. Okay, so example program, how a program might, again, we caveat everything with might in this video because, it's subject to change, improve, or whatever with C++. So interestingly, let's just take a look at this. So every file, let's see, could be part of a package. This is sort of like Java and D and tons of other languages that have things like packaging together. It looks like a module system. Let's see, classes, again, we get the variable type, leading. Okay, so that's a little bit different than the CPP2 example or the Pascal style variable name. Again, I like these short variables, float 32. That's nicer to type, and I know exactly the width of the type here. Again, I think this in modern languages is one of the things that is really nice. Now I sort of appreciate in languages like D that an int is just always 4 bytes, because for a beginner that sort of makes sense. You type int, integer, I know what that is. You don't have to explain like what bits are and sizes and stuff. Although that's pretty trivial to sort of like, I shouldn't say trivial, but that's something you can understand relatively quickly when you're starting off. But it is another thing to think about. But I still like this when I'm programming to just, type this out and know exactly that types. Let's see, we got the functions for the prefix. Again, kind of nice. You can, search and grep for these things. So I tend to think that's a nice thing for the design. It probably also simplifies things on the compiler end for like parsing. So, not everything, is a mixture of like, you don't know if it's like a function pointer or some like functor or some weird thing, right? This is a function definition. That's all there is to it. Let's see here. Then you got the type or the variable name. An interesting slice. So I wonder, yeah, that's like a span here. So you're getting a view. And then let's see what else here. We got our variables here. Var looks like it's going to be similar to auto, right? It's just deduced. I wonder if they do, this would be a really nice thing in the language. And you could correct for this in these languages like Carbon or CPP2. If you do like the functional style thing where you have var for things that can mutate and let, well, I guess it depends on like the functional language, but something like that, like, var is the mutable thing. It's variable or variational or however you want to think about it. And then let would be like the const, thing that you can't change. That would kind of be nice to just have that in a keyword, one word that you type, or actually just use the word like immutable or something. Or read only, or just there are opportunities to fix things here. And I'm sure folks are thinking about that, right? We'll read the actual Carbon doc. Let's see, here's our loop here on this side. Let's see if I can't highlight it on both sides. But we got a range for loose for circle in circles. And then this is the type here. Okay, so that's what we're going to call it here. And refer to it as C. You get the radius. Okay, so that's basically like this, your range-based loop here. Let's see, interestingly, the default is accessed by const ref. So again, maybe there'll be like a keyword here like ref or something, or mutate or whatever you want to call it. Print, standard print, love that. In C++ 20 or 23, we get to print, which is great. And let's see here. We got main with the trailing return type for the i32. Again, the integer with 32 bits. Let's see. Dynamically sized array like stood vector. Okay, so actually telling us here, var circles, you just call it array. Interesting here. What is a fixed size array? I wonder if there's a different name or a different type for that. Call it like fixed array or something. Again, vector, I think, I don't know the exact origin of this in the C++ language, where that came from. I don't like vector because, again, as somebody who does like graphics and game programming, you confuse it with like mathematical vector, so it kind of means something. And you'd rather just call this like dynamic array or something, which I guess that's what we have, like array or resizable array or whatever. So anyways, that's probably what you're going to be using. Or maybe an array where you just have like the fixed size or something. So anyways, this is just kind of interesting syntax. But of new things here, let's see, .r. Let's see, for our circles, we're just creating 2, and these are the like fields that we're initializing for it. Okay, that's cool. And then we can implicitly convert array to a slice. Yeah, this is something that, again, D, which again, as you folks know, I use. That's like my number 2 language. as far as usage in my total career. Most of my career has been C++, but I use D a lot now. Slices are really nice, which are like views or spans into a structure here. And I think that's just the right way to go. It's hard. A lot of modern languages also have slices. It's hard when you start using slices to not have them. Of course, in C++, the way that you have them is exactly as here for print total area, where you have a span or a view, non-owning view into some data structure. Okay, that's the way to think about it, or just a span, which is usually a pointer to that, and the length as well to that structure. So okay, this looks interesting. Let's see. So that's the Wikipedia language. Yeah, and you can see the comparison here. C++. I would put in CPP2. Even though it's not specifically marketed as a successor language, right? It is, both of these are going to be useful for evolving the C++ language. In fact, if I remember correctly from the 2022 talk, because that's the one I remember I watched in full, the worst case with these successor languages, Carbon, CPP2, Hilo, which is formerly Val, although that's sort of like its own thing, I guess. Circle, another language maybe we could take a look at if we can get a hold on it. They're going to evolve and push the C++ language to say, hey, this is possible. So that's the worst case for these successor languages, which is kind of neat. It's a very exciting time in systems programming and for C++ programmers. So let's look at the Carbon GitHub. That's the first hit here. Let's see. The rest of these are just like YouTube videos and other stuff. Okay. As expected, because yeah, this is a very early project. In fact, we're seeing commits like, 2 days ago. I wouldn't be surprised if it's Sunday that I'm recording this, so you're probably not going to see any commits in the last hour here. But anyways, let's go ahead and take a look here. Okay, so you got the announcement video. Let's see. We got the why here. Is that a separate page? No, that's all here. Okay, so we'll go down through this page here and take a look at it. Let's see if I can... I don't know why it's sized weird, but that is what it is. Okay, anyways. Let's see. It's fast and it works with C++. Performance matching C++ using LLVM. Again, you get low-level access. It interpolates with your C++ code and scales with your builds. Okay, so that's cool. Let's take another look. We get another look at the language here. Let's see, is this just an image? Yeah, we can take a look at quick sort and some of these things. Okay, I'll hold on to this for a moment. But we're seeing a lot of the similar things here. I mean, obviously a much more concise syntax here. And this is going to be the secret. I mean, this is the same thing that we're seeing with TypeScript. I think more people are writing, probably more people are choosing to write TypeScript than JavaScript, which is kind of interesting. So you can always go down to the original raw language, but yeah, this looks very concise, right? Like ever since we got things in C++ like range-based for loops, those have been very amazing, and we can make them more concise. We have our fix with types here, which are easy to access, which encourages us to use them without having to type like std : int 16_t or these crazy things. So that's very nice here. We've got slice in the syntax, so then people are thinking about what's a slice. Okay, that's a span. I just need to view it or whatever, and not make copies of things or whatever. So again, building these things into the syntax is very important for these concepts to be used. These things that we're finding out as programming evolves are very useful concepts. So this is very nice here. Or at least I like where this is trending amongst languages. Everyone has their preferences though, so you may or may not like this. Let's see what else we got here. So it's modern and evolving, solid language foundations that are easy to learn. Yeah, I mean, there are probably things, again, too, here that are going to be easier to learn in C++. Then you can always watch my old videos. Someday they will become old, I guess. Be like, how does this stuff work in C++? So anyways, that's kind of interesting here. So let's see, we got an easy tool-based upgrades between Carbon versions, safer fundamentals, incremental path toward a memory safe subset. Oh, very interesting. I mean, we've got things like move semantics, and I wonder if they're going to have an ownership model here. Let's see. So let's see what else is going on here. Now, this is an important part, too, I think, of the evolution of the language, and it's sort of emphasized that it's a welcoming open source community, again, because you want these projects to grow, evolve, and be successful. So, again, I think this is really important towards the mission, right? They're stating this very clear. So that's kind of neat to see. And I just like that, right? I love open source stuff. I think it's really important for software. So let's see. Community that works to be welcoming, inclusive, and friendly. Awesome. And then the batteries included approach. Compiler, libraries, docs, tools, package manager, and more. Yeah. I mean, any language these days, you're kind of expecting folks to have this stuff. I mean, I see this in university where, we could kind of... I like to teach things from a first principles approach where you have the compiler and are able to, understand how things work, right? We don't want to hide stuff, but you do want some tools for giving resources for folks to fix bugs or, write better code because you want to know how to do that stuff, as directly as possible. You probably want things like a package manager to get things set up. I mean, the ecosystem is important for a language. There's no denying that. As much as I'm a build from scratch person, and I like building things on my own, it is nice to have a singular package manager from the start. You can always have more, right? You can always add more, but have an official one that's part of the community. I think that's going to be useful. Documentation, super, super important. And again, having some good libraries so you can build stuff and get started, right, is useful. So anyways, I think we know these things, but just interesting. Most modern languages, it's this is the list. You have to have these things. And the folks working on Carbon, they know this, right? The folks involved with this project are experienced software developers. So it'll be interesting, and we can learn a lot about them. So again, the why, C++ has been a very dominant language for performance, right? Quantitative finance, gaming, scientific computing. That's where I think it's going to continue to stay strong in those domains. Not that it only has to be, you can write awesome software in other languages, but, different languages, again, have different trade-offs. And C++ is optimized often for the performance trade-off, right? It's not always for readability or writability. It's for having a stable API and being fast. That's sort of the trends here. So anyways, let's see. They're saying it's struggling. C++ would be struggling to improve and meet developers' needs as outlined above, in part to accumulating decades of technical debt. I mean, C++ is a language that, let's get the date right here. If I bring in the wiki and search C++, let's see, we can trust Wikipedia, right? We've got, 39 years. Okay, I was thinking it's even older than that. Let's see, Bjorn might have even been writing C front. Yeah, C with classes, 1979. I was thinking it was even older. Yeah, 85. So I mean, it's 45-ish. 39, depending on how you want to measure this, to 45 or 46 years old. Any project that's old is going to accumulate some technical debt. And in some ways, it's kind of done a good job when you think about a code base that's that large. Now, that said, I don't maintain any compilers, although I've done some work in LLVM. And that is a big code base. So, there needs to be some improvements here. So anyways, incrementally improving C++ is extremely difficult. Let's see what they say about that here. The difficulties here. They have an explicit section. Yeah, things like technical debt, prioritizing backwards compatibility. I mean, this is a big debate, I think, in the C++ community, if you should break ABI. It's a big strength that, for someone like me that's been teaching, that I know my code's going to run forever, and I can sort of teach students that this code will work, and you don't have to use different versions or additions or anything. But with that said, that has something to deal with the evolution, right, of the language. So it's a very interesting discussion. I don't know which side folks fall in the ABI discussion. And there's ways to write your code where you can kind of protect yourself, right? Like the pimple idiom and passing structs as arguments so you can change things. And there's little tricks that you can do in designing your code base to protect yourself and your API. But the ABI, the application binary interface, let's see here, how things are structured, what guarantees you have, calling conventions, these types of things, a little bit trickier, I should say, than the API here. Let's see. Yep, let's see what else is there. Sorry, I clicked off of that. So anyways, yeah, you need like a successor approach. Let's see here. And then the evolution process. Okay, so this is the other stuff that folks are mentioning. Beyond C++'s evolution direction, the mechanics of the process also make improving C++ difficult. C++ process is oriented around standardization rather than design. Interesting. Yeah, this is kind of interesting. You sort of want there to be a standard in the C++ language because compiler implementers are some folks, right, that rely on that, need a standard to build their compilers. And then some of those compilers need to be certified for domains like automotive, which, you know, C++ is also used so that we know they're like safe or there are certain guarantees. But yeah, you want there to be something for the design and evolution. Interesting. Yeah, it uses multi-year waterfall committee process. I wonder what folks think about this. This is a separate video, I should say. Waterfall and agile stuff, you know. The 3-year model. So C++ evolves on a 3-year model, roughly. So that's why you have C++ like 11, 14, 17, 20, 23, 26, etc. And I've worked in both agile and in some waterfall places. And for projects, especially where you sort of have to get things right, waterfall is a decent way to go about things, right? To try to design as much as you can up front. Now, of course, you're doing that by committee with a bunch of vested interests. So again, there are just interesting things here that are sort of fascinating to study. And, I observe from a little bit afar, occasionally chat with folks about these things. So it's interesting to think about what the right process is, like which language has got it right. Again, there's only so many languages that have been around for 45 years. And really since the standardization, I guess, of 98, and maybe there was a standardization earlier, 85 is when it said it first appeared, I guess. But for how to do these things, I mean, it's an interesting challenge. So yeah, these are some reasonable difficulties for why to take the successor approach here. So anyways, let's kind of keep moving on. There's a lot of interesting things, I think, for folks to think about in the community here. Let's see. Existing modern languages already provide an excellent developer experience. Okay, and they highlight Go, Swift, Kotlin, Rust, and many more. Developers that can use one of these existing languages should. Okay. Oh, all right, sure. And we've looked at on this series Go, Swift, Kotlin, Rust, and many more. All right. So check out all those if you want to go ahead and see. And yeah, as mentioned in this document, all these languages have like package managers and ecosystems with build tools and static analysis and all these different types of tools incorporated in them, which is really neat, and I think they are useful. And I think this point though is like the developers should use one of these is because they are like mature languages. So let's see what they say here. Unfortunately, the design of these languages presents significant barriers to adoption and migration from C++. Okay, yeah. So going from C++ to say like I don't know, pick any one of these languages here, right? You can't just translate your code base. I mean, you can try doing this, but again, if you took the time to build your language in C++, you probably did that because you were all in on performance. Now these are all like systems languages, and I think I guess Kotlin maybe does systemsy stuff. I don't know if that's how they market it, but yeah, I guess there would be. I don't think folks would argue against there being challenges migrating code to these languages and getting the same like performance and portability guarantees and stuff. So anyways, that means, yeah, Carbon took a successor approach, right? They didn't just say, hey, we're going to just translate all of our code to some other tool chain here. Okay, so interesting here. So it's designed around interoperability with C++. as well as large-scale adoption and migration for existing C++ code bases and developers. Yeah, so as mentioned from the Carbon Wiki, this project is open source and started from Google. So yeah, if there's a place that knows about large-scale development, Google's a really large code base, and they do a lot of things at scale. So there you go. So, the folks collaborating at some of these places would know what's going on, I guess. Okay, let's see here. A successor language requires, let's see if we agree with these. Performance matching C++, yeah. Seamless bidirectional interoperability. Yeah, I mean, this is going to be the key for this Carbon or CPP2 to make sure that, you can't just translate one code base to the other. There's got to be like an interop and a transition over time here. So any library working in a C++ stack can integrate with the Carbon stuff. Yep. Gentle learning curve. Yeah, I mean, here, let's highlight this point and look at some of this code here. I mean, I think this code looks reasonable. I think you can look through it and say, this is nice, it's less to type, I sort of understand what's going on. Yeah, you do have to learn the programming stuff, like what movable is and slices and so on. But I don't think that's, anything too unreasonable, right? And right, in C++, we have like string views and spans, which are like pretty similar. And really, you probably just want like a slice to look at that thing. So, it is kind of nice, right? There can be a lot gentler. I've had time to learn. So any new language should be able to learn from another language. And again, I'm not saying that just necessarily makes it 100% better, but there are opportunities to learn for sure. So you want comparable expressivity. One of the things C++ does do well is it does let you write code in many different paradigms. That's been a thing since C++ 11. You can write functional code, generic code, and do sort of generic programming, various capabilities. So that is kind of nice. There's concurrent patterns and so on. So anyways, that is nice. But yeah, you want to be able to solve the problem in different ways using different paradigms. Let's see, scalable migration with some level of source-to-source translation for idiomatic C++ code. Yeah, okay. So anyways, yeah, they're looking at it like this. JavaScript to TypeScript, Java is to Kotlin, and C++ is to Carbon. Okay, so I think we sort of get the idea of, Carbon supporting all these different goals that C++ has with more safety, easier to read and write, an easier language or sort of fresh start so you can evolve the language, right? And we basically want a lot of these different features that other programming languages either have had for a long time or are getting, things like pattern matching and reflection and so on, and safety things like, Rust coming to mind here with their, borrow checking mechanism and being able to, because of that, being so like baked into the design, have a compiler that supports that and can make various guarantees for us. Okay. Let's see. Other non-goals, notably including stable API. Yep, I think that's important. Perfect backwards or forwards compatibility. Okay. Let's take a look at the language status here. It's an experimental project. Yeah, there's no working compiler at this point or toolchain. You can see the demo here. So we got the demo. We will try some examples. However we can. And let's see here. Okay, so we're going to have a lot of the same stuff. Generics, class types, inheritance, operator overloading, code organization, modular structure, etc. Okay. Let's try this out here. And again, here's the gentle learning curve. Yeah, I think this is an example from the Wikipedia. Okay. All right. Let's just take a look at a compiler explorer example here, just to get a little bit of code. And I want to get you excited about like trying this out too. So let's just look at this for a moment here. This is the Carbon example here, and it does work. It is returning something. Okay, so we got a package. Okay, sample API, square, returns I32, return x times x. And we have our main with a trailing return type, and then we just return this value here. Interesting. I'm not sure what the compiler is doing here, though. CPP2, right, we could clearly see there was like a translation. Interesting that this is what's generated right now. Yeah, we don't have options yet for like seeing the binary again, because there's no like, again, this is like not even version 0.1, which I said, but kind of interesting to see what's going on here. I wonder, yeah, what kind of machine are they building here? I mean, I'm assuming, one approach is to just transpile down to C++, but it looks like they're doing something that's going to be compatible here. I don't exactly know how to interpret this here. And maybe there's some talks about what's going on the toolchain side. Okay, so we'll have to try this out. At least we can try this, but here's what the language looks like. I don't know, let's write our first like function here. Let's call it hi. I'm going to take in an x I32. Is void a thing here? I wonder if it's like void or empty. Let's see here. Void, or maybe it's none. Let's see here. I'm just guessing at the syntax. Return. Let's see. I wonder, did they have auto? Let's see if that works here. I think they had print. Hi. Let's see here. Okay. Let's go back to our wiki page. Did we have... Oh, I guess just like no return type. Okay, so there's no void. Hey, I like that. Print is capital P, and then we got the same thing as like format. Okay. Okay, let's see. Here, let's just get rid of that. We don't have to return void if it's not returning anything. And I can just use hi x. Okay, let's see. Does that work? Oh, I gotta call it, I guess. Hi 42 with a semicolon. Okay, we still got our semicolons in our successor language. Make it sure it's official. Oh, let's see. Do I have to tell it's like the 0th thing? Yeah, hi 42. Okay, cool. We wrote our first little function. That's reasonable enough to do here. Okay. Okay, now let's actually look at some of these features here. So let's see. So Cartman's going to provide a modern generic system with check definitions while still supporting opt-in templates for seamless C++ interopt. Check generics provide several advantages compared to C++ templates. Okay. So what are these? They're fully type checked, removing the need to instantiate to check for errors and giving greater confidence in code. Okay. Avoids compile time cost of rechecking the definition for every instantiation. Interesting. Let's click on this here. What's this mean here? Generics. Okay. So we know these are a mechanism for writing parameterized code on the types, right? And generic code is, how to say this? It's almost like good generic code is kind of like the algorithms that you see in an algorithm textbook, right? You don't care about the type. You just see quicksort and it's sorting something, right? That's a good algorithm, right? You can use it for everything. That's sort of how you want to think about generic code. It's like the ultimate. You're stripping away the types that are needed, and it'll just work. That's what's kind of cool. I mean, that's why folks kind of like the dynamic types and stuff, right? Everything's kind of generic. But it turns out type safety is pretty good, so we do like that for actual code. Okay, so let's see. What does this check type system mean? So, okay, for example, instead of having one function per type, you can sort something like this. You may have one generic function that could sort any array with comparable elements. Okay, so here you're just like, I guess this is maybe like concepts or template constraints in D, concepts in C++, where you're just saying like anything that's comparable for your type is fine here. Okay, you can sort that type of vector here. Okay, now I guess, and they're going to check that by default, compile time parameters are checked. The template keyword may be added to make it a template generic. Okay, interesting. I mean, I guess this is what you want. You just, again, want your code that just works. And again, I guess I don't understand what the template... let's see. I mean, by default, let me say it this way. You want anything that can be done at compile time to be done at compile time. You don't necessarily want to have to specify all the instantiations, right? This is where like class template argument deduction in C++ is really useful to be able to just deduce this is a vector of integers, for example, and not have to supply an int, right? You just look at what's inside of it and see that everything's an int. But I guess I don't know. Let's see here. I guess I'll have to think a little bit more about that checking. Now, if these are just the constraints, then it just means something has a comparison operator, so whatever this like comparable thing is, and it just works, that's fine. That seems fine. These are like concepts. That's the right approach. Yeah. Let's see. Enables automatic opt-in, type erasure, and dynamic dispatch without a separate implementation, which should reduce the binary size. Okay, cool. Enable constructs like heterogeneous containers. Yeah, can my vector contain, different things? It's, that's kind of cool. Let's see. Strong checked interfaces mean fewer accidental dependencies on implementation details and a clear contract for consumers. Okay, yeah. I mean, yeah, strengthening the generic system. I mean, could you imagine if, I think generics are important for sure for writing code. Having them type checked and the constraints checked is going to be really important for the safety. And I'm just imagining if we had this kind of stuff in like C++, like, the old language or whatever, because you're seeing these types of things in newer languages, and it does make a difference for like libraries. It can make a difference in the types of errors. Right. Let me give another example of what I think this means here with a modern generic system. If let's see, here we go, supplied a type here that didn't work, I don't want a whole large, list of messages for why this doesn't work. I basically just want to know that this type doesn't have this comparable operation implemented. And you could just like print that out as error message. So you can get nicer error messages with this type of thing, I think, which is kind of neat. Okay, so that's kind of cool. Let's see. Here's the big one here on memory safety, because that's been the thing that C++ is under attack for these days, which is kind of interesting because there's sort of mechanisms in C++ for doing, safe memory accesses. Whether you're doing things with like unique pointer, if you're using any pointers, the language becomes relatively safe when you start using that. Right, you can keep things on the stack. You can use static analysis to make sure that things are default initialized. I mean, you sort of start taking care of these problems. Now, where you do have to be a little bit careful is, or even extra careful, I should say, is concurrency, where we don't have defaults for like thread local, data. For instance, you might want things like const and immutable to be transitive. So those are a few things that come to mind for memory safety. Let's see what else is going to come up here. This is just the Wikipedia of memory safety errors. And then, of course, I mean, you have your like classic, like, like use after freeze and deleting stuff, and not using RAI and an exception being thrown, and like, you don't freeze some resource, if you have exceptions in your code. So you basically end up making everything like no except, or, to try to like catch those errors and make sure you don't go on like some weird like code path. So let's see. So they're going to try some things like tracking uninitialized states better, enforcing initialization, hopefully just having like one or two ways to initialize things, because again, that is kind of like tricky. And not saying it's as much a problem with memory safety, but it certainly can be an issue. But things like casts being explicit and making sure that you don't have implicit conversions and stuff, which could cause problems. Those are all like important things for building a little bit of a safer language. Bounds checking, another, like, you do bounds checking, check for uninitialized variables. That knocks a lot of vulnerabilities, out right there. I mean, you get those two things. And then you add some of the memory safety things with like making everything a unique pointer. You're in a much better spot. Your code's gonna be harder to get in a bad state, I should say, right? So, you avoid sort of various leaky abstractions that can cause problems. Let's see. So having a default debug mode, okay, that uses things like address sanitizer. Yeah, that's what you want. You kind of want to be, a lot of folks are using these tools like ASAN, address sanitizer. UBSAN for undefined behavior, sanitizers, thread sanitizer, and so on. So folks are using these tools. If there's ways to make them cheaper and easier and faster to use in your builds, because some builds take a long time, right? And you want to be able to run these analysis, that's very useful. So I'm excited to see how they're going to get this stuff here. Okay, so we're at the getting started point. We have 20 minutes or so left of this video. I have no expectation that this is going to work since this is not even a 0.1 build here. But let's try it. Let's try out the instructions here. Let me open up a terminal. And we're just going to follow along here. Let's see. Sudo apt update. Super secret password. Okay. Oh, we're using Google's build system here. That's cool. I've never downloaded that. I should have LLD, but yeah, let's update it. Copy, paste. Unable to locate this thing. Sudo apt get install. Okay, we might not be able to do this here. Build dependencies. Oh, you need to install our build dependencies. Let's see what's going on here. How do I do this? Sudo apt update. Did it not update? Okay. How do I get Basil? Let's see here. Maybe I can just do this. Let's not give up yet at the first step. let's try to install it here. Okay, I gotta add the apt repository. I'm on 22. So we can follow this here. Okay, it's gonna do the right thing. I'm gonna trust it. I'm gonna sign. I think if I get that, we'll be okay. Because I think some of you folks are gonna want to try this out, so we should at least try here. Okay, we gotta do a full upgrade here. Okay, so it's unpacking and setting up. For those who don't know, Basil or Basil, I don't know exactly how to pronounce it. Yeah, we can install it, and we'll install version 1.0. I believe this is Google's build system. It looks like it's been internally built, and there's a conference on this. So a lot of our programming languages, we look at conferences. Okay, so it's a build system for open source projects to build and test your multi-language, multi-platform projects. Cool. Maybe it's better than CMake? I don't know. Let's see what it does here. Maybe we'll find ourselves a good build tool here that we have to check out here. Interesting that there's a full conference for it. That's kind of cool. That kind of makes it very productive too. In the sense that we want build systems that just work. So if there's folks gathering to get build systems to work, I'm in support of that. So that sounds good to me. Let's see here. Okay, we're at 60. Okay, it's updating other libraries. I'm going to pause this and we'll jump in 1 second. All right, so there we finished our full upgrade. Sorry, I just paused so we could do that. Let's go ahead and make sure we install if we haven't already. Let's see, depends Python, but it's not installable. What have I done here? I guess it's available. Okay, maybe it did install. I don't know what happened. Let's go ahead and try our Carbon installation here with the rest of the other tools that we need. See if we can get this interpreter running here. Yeah, sure, install everything. I don't know what version of Python we're using. We're getting lib C++14. The cool thing sometimes about looking at these projects and playing around with them, and maybe it's best to install these on a virtual machine. I'm on a home machine, so it doesn't really matter. But it is kind of interesting to, let's see here. What am I going to say here? Just play around and see what sort of the state-of-the-art stuff is. This is how you pick up information about like different build systems and stuff. So again, I'm just going to follow their directions here. Let's see. GitHub. Okay. We'll get everything installed here. Interesting. Pre-commit. Okay. Oh, maybe let's do these things one at a time here. Here. To authenticate, run gauth login. Okay. What account do you want to log into? This one. Yes. Log in. Okay, I'll do this here. Press enter to open GitHub. Okay, I'm gonna do this secretly. Okay, that seemed to work. Let's see here. What else is the next instructions? Where was I here? CD into carbon lang. Let's see if we got it here. Oh, I guess we didn't. There, we're authenticated now. Cloning. No repo found. Wait, did this work here? I think we already did this. Set up Git if you don't already have a fork. I guess I could just download it here. Oh, there it goes. Okay. I don't know what happened. Let's CD into it. Let's run this tool here, pre-commit. Okay. Let's run some tests here. All of them. Okay, cool. I don't know. This is some of the stuff that you just kind of use at scale. You have like different build systems. There's like, I've done some continuous integration stuff, and a good way that you could practice if you're not familiar with all this is to try using like GitHub Actions on your repo. You get free minutes. That kind of gets, some experience of building tests and stuff at scale, just as we're sort of waiting for this to run. So anyways, that could be some interesting stuff here. Now I wonder if this is going to build a tool chain or give us the interpreter. That's what I'm looking at. Otherwise, we're just going to go to the Godbolt and play around a little bit with the language, with what we can, with whatever code we can find in our examples. We got a few examples here that we'll try out at the least here. But let's see if we can get those working locally. Okay, we got a lot of like tests and stuff here. Let's see, is that correct? There's going to be 17,000 tests. Is that right? Lots of actions. Okay, some stuff failed here. That's okay. I probably just don't have the right like stuff. It's the weekend. This is a 0.1 or less project here. Let's just go to Godbolt and try out a few of these examples because we know that's working. And we don't have to worry too much or panic. But I think this is interesting to try to build and learn about some of these tools anyways. So anyways, let's look at the examples here. Let's do, let's try quicksort out. That's always good. Let's see what happens here. Okay, so let's just start this one. We'll keep our main here because that's going to come in handy. Let's put this in a package. I wonder if packages are going to be by... here, let's just return 0, just so we have something. Packages are going to be like by directory structure or something. You don't have to be in C++, but there's different constraints I guess you could have here. Let's see, partition. Okay, so this is the generic or check generic here. Comparable and movable. Okay. Let's make this a little bit smaller here. And we want a slice of whatever the type is here. Okay, and it's going to return us an I64. Interesting. Okay. So let's see what we get here. Create a variable I64 equals -1. And then let's see, we get our range-based for loop here for each of the elements, T and S. If it's not equal to the last element, let's see, we're going to have to kind of like parse this here. Then we can do a swap. Okay, and we still got like the C++ stuff here. We're taking the address of whatever the element is at the ith index and whatever the element is here in this loop here. Now, interesting, I wonder if this loop, I think I saw it in the wiki example. Let's see here, where we had the range-based loop. What did that translate to in the C++? That was a const reference here. But I guess swap can work with that in the language. I guess that's okay. Interesting. Okay, let's see what else we got here. Okay, and then we're going to return I. Okay, let's see if that gets a compiling. That should be the partition function as it is. Yeah, again, these samples might not be up to date with what's on like Godbolt, so who knows here. Let's see what kind of error messages we're getting here, if any. Unexpected semicolon. Expected API or implementation here. Oh, is that for this here? Maybe I messed that up here. Oh, only I-32 is supported for now. Okay. We gotta work with smaller things that we want to partition here. Okay. Let's see, that should work here. Unexpected write only curly brace at line 10. Prep for a semicolon. Could not resolve comparable. Okay. Comparable. Again, this just might not be ready on Godbolt, so we might just have to look through these examples. At line 3. Yeah, I guess the check types. I mean, okay, maybe that's a bad example to start from, because that getting your type system right and figuring out these things is probably one of the harder things to do here. So interesting. Let's look at, well, let's, you know what would be interesting? Let's just take a look at, I think it'd be interesting to take a look at the C++ and Carbon examples. Yeah, let's look at, well, we've got the quicksort version here. Actually, if I paste this in, I don't think it's ready here in this Carbon example. Oops. Here, let's just do for the main. I just want to see if that compiled. Or let's see, can we get rid of the... Oh, interesting. This is just something I noticed about the syntax. This is in the brackets here. That's actually a really nice syntax here. Let's get rid of it though for now if that's not supported, and see if we can just get something out here, which would be kind of interesting, just to see if it builds again. Oh, I think I just messed up this thing here. Okay, so that's still evolving. I-30. Oh yeah, I gotta put the I-32s in. That's kind of funny. I-32. Yeah, but it won't be a hard. I mean, that's not a hard thing for them to change when the time comes. Have them just get things working. Source. Okay, unexpected semicolon at line 21. Oh, interesting. Another thing that we noticed. Okay, so there is a let syntax here. I talked about that at the very start. I wonder if that is. I wonder if they are doing something with like immutability or making that const or something. Like I think in functional languages, let is always more like the mathematical, like let p equals this and p is that forever, or you know, for the scope of this function. Okay, cool. Syntax error, unexpected, colon. How do I declare variables here? Var. Oh, maybe I could just change it to var if that's not supported quite yet. Again, it's very much in design mode, so that's okay. This might be the earliest. Between this and CPP2, these are the earliest languages. I'm not expecting anything to work. So I'm surprised we even got a hello world working. Syntax error, unexpected, colon. Maybe we can just kind of hack this together here. P equals. Now this might not be okay either. And let's see here. Var p I32. Probably have to initialize it. Equals 0 or something. How did I do it here? I'm gonna cheat and copy and paste and just call this p. Let's see here. Oh, so at line 22 now. Oh, I see. That's the slicing syntax. Okay, cool. I mean, again, these are like with the slices here. I think, here, let's put some spaces just so you can see here. P+1 would be like, you know, to the end, and this would be like from the start to the range here. Can I just put like 0, and I wonder if there's p.length or something for whatever that collection is. Oh, sorry. This would be s.length or something. Let's see here. Now I'm just kind of messing up the syntax, I guess, but that's what I imagine it's going to be, something like this. Okay, there, quicksort. I guess it's evolved a little bit. Yeah, let's look here. Let's see. Let's get this example. Ooh, hold on. Let's go back for a second. Let's try to run just this one here. See if this is working. And the packages might be different. The Godbolt version might be different from what's actually meaning newer or older. That says trunk, but we don't know if that's true or not. I don't know. API? API is a keyword? Interesting. Okay. At line 3, import math stuff. I don't know. Oh, that's just the import statement, I see. Okay. And only I-32 supported, so we got to switch those around. And that's at line 6. Okay, okay, so our circles have to be integers. So this is going to become a problem. Let's see if it catches it. Right, square bracket. Okay, anyways. Okay, so 0. What's it expecting? I don't know. Okay. Well, I can't. It doesn't look like we can run. We could run some of those examples. I mean, it had a little example for us to start there. Anyways, let's just continue looking at the language. The example I do want to look at here that is on this page here, as we're wrapping up, that I think will be interesting, is mixing stuff. This is pretty ambitious in the language here. So I'll be really curious once we get to version 0.1. Maybe we'll revisit this if folks are interested, so we can actually try to run this and see how this interopt works, right? We can see where there's a struct here. Like, I guess it's just going to work. It's just going to, if it doesn't parse as like Carbon code, it's going to parse it as C++ and see if it works or something. That's a real interesting engineering challenge. I would have to sit down and think about that for a long time for how that works. Some languages you can kind of get away with it, and I mean, personally, I would just cheat and I would do like the inline assembly thing. I'd have an inline block to make it easier for myself. But if they get this working, that is true interoperability. So again, you know, there's a reason why there's folks working on Carbon that aren't me, because, you know, that's a big challenge, and you need a good team behind this stuff to get it working. So anyways, I think that's pretty cool to see this interrupt here, right? Because, you know, some of us have spent years working in C++, and we don't want to just lose that knowledge, so it is nice if we could just do stuff and then maybe use the convenient Carbon way. And then, of course, I imagine, you know, new projects that are started could just be like pure Carbon, and then you can call your C++ libraries. And that's how you sort of like migrate to a new language here. Okay, let's look at a few other things here, since we're not going to mess around with the code. First and foremost, there's been a lot of conference talks. I anticipate there will still be some, so, you know, keep an eye out on announcements. I think there might be a Twitter or Mastodon, or you could follow the folks involved with the development who might, you know, give some updates about these conferences. There's a Discord. That sounds like the best way to probably get up-to-date information here. And there's ways to contribute to this project, which is cool. So again, if you are a compiler engineer, or maybe just somebody looking for a way to contribute, they're marking things that are good first issues to work on. Just let's take a little tiny look, because we didn't get through all the design stuff. Let's see some of the other things here. So there are interfaces, which we don't necessarily have in C++. Right? You have like pure functions that you have to override, but yeah, we probably want interfaces. That's been a nice thing here on other languages, and it is sort of as you expect here. Kind of cool too. The thing that we really need in C++ are these interfaces where we can have like comparable or something, and just have a bunch of these functions like less that you have to do if some type is comparable. I mean, this is a nice way to have interfaces. When you have languages that are designed with single inheritance, for instance, but multiple interfaces, that you could say like, here's a data type, a point in, you know, 3D space, but you have to have functions for like comparable and copyable and like these types of things that you have to implement. That kind of makes it nice and clear that you're coding to the interface. I like that style. I generally think that's good, and it's kind of like coding to a contract, so you know what your types have. Let's see what else we got. This is more interfaces stuff. Facet or faucet types here, however you want to pronounce that. To type, check a function. The compiler needs to be able to verify that uses a value that matches the capabilities of values types. Okay. So these constraints are represented by type T. Okay, so these are like the facet type. Okay, so I mean, they're using this example of like comparable. That means if I have a type here, I need to, I can basically just say that type needs to adhere to this interface for comparable. So that's another advantage again when you get these interfaces, I guess. That's actually a really nice design. I like that. And you can see that here, right? We're just putting that interface like on this type that says, yeah, it must be, whatever the thing happens to be, it must have this comparable thing implemented from that interface. That's cool. I guess you could do the same with parameters. That's this little bit here, which is cool. Make sure something's printable. Yeah, this is a great way to have generic code. I like it. Let's see, you can combine interfaces, constraints. Let's see if there's other stuff here. I mean, it looks like they're focusing a lot on the generic programming to make it easier and safer to use and to write code here. Okay. I'm pretty happy with looking at this. I think it's a nice project, and, you know, hats off to the folks who are attempting to do something that's, you know, potentially going to either evolve the C++ language for 26 and 29 in an interesting and better way, or otherwise come up with a successor language in the same way that we have. If I scroll up here, let's get to the analogies. All the way up. You know, this sort of relationship with C++, where most of your folks just write in Carbon, like a lot of folks write in TypeScript today instead of just writing in JavaScript. So, well, there you have it, folks. You know, we've gotten about an hour here. I'll be really curious to hear your thoughts. We've had a lot of good discussion on the CPP2 video, for instance, on just looking at the language and what's available in it, what's going to be new, and different ideas. So for this particular video, again, I'll say. Again, probably the earliest. This might even be earlier than the CPP2 stuff. So it was cool to see some of the examples that we're able to get running in some of the sample code and play around with it. And this might be just a really interesting project for those of you who are interested in compilers to see like how something evolves, how you sort of like design these major. You kind of have to pick when you design a new language. What are going to be the really important things? Like, are they going to be memory safety? Doing things with generic programming as we sort of, I mean, that's the thing I kind of fixated on, I guess, in this video. But, those are kind of the things I imagine that you just have to make design decisions about very early on, because they'd be hard to kind of glue in later, right? And the job of this language is to try to fix as many things, right, as possible for that 1.0 version, right, in 2027 or 28 or whenever it's going to come out. And have some major impact while also having a ecosystem that can evolve and so on. So it's a great engineering challenge. I'm really excited to follow the developments. I hope you're excited about it. Even if you're not a C++ programmer, again, I think it's interesting just to see the design decisions, what things they try to take away, because at the end of the day, and through this series, we found different languages borrow different things from other languages, right? And that's how the evolution's progressing. And we're really in an interesting programming language boom right now, where there's lots of languages, probably more languages at this time people are programming in, right? It's not just C++ and Java and Python, for instance, right? There are many, many languages, and companies and universities and stuff are opening up to like, let's teach a course in this language, or let's build a commercial project in this other language. So I think it's a really exciting time to see what's going on. I think Carbon's one of those exciting projects to see what happens with it, how it evolves, and folks can even get involved. Maybe some of you will. So anyways, folks, I'll look forward to your discussions on this video. Thanks for your time and attention. This was another video where we went over an hour here. So thanks for those who made it. Let me know if you made it here. Put a little like hashtag Carbon or something. And I'll look forward to seeing that. Anyways, folks, thanks for your time and attention. I'll look forward to seeing you in the next one.